Hello, welcome. This is Birdy. Welcome to a new lesson in Houdini. Today we will continue our journey in the new series Sea Monster in Houdini. So today we will dig deeper in the whitewater simulation, and we will explain many parameters in the whitewater solver. So let's get started. So let's continue, guys. Now we are in the whitewater simulation. Okay, now we can see the particle of the whitewater, right, as a particles. Okay, let's see it. Of course, it takes time because we didn't cache the whitewater source, so it will take little time to caching. But if we want to see a fast whitewater, we should cache the source itself. So as we can see here, now we have let's first hide the grid. Okay, now let's talk a little. This is a whitewater object. Here it import two things: the volume source, okay, and the whitewater source. The whitewater source and the fluid compressed cache as a volumes out. Okay, we can control the emission amount and the whitewater scale. We can control the voxel. Let's make the voxel much smaller, 0.1, to give us more resolution. And we can control also the amount of the emission from here. Amount of emission, if it is 1, any number we put here, we multiplier of the amount of the emit water, right? So if we put 1.5, it will multiply it in 1.5, the emission amount. Okay, one is fine. Velocity offset. I usually like to put 1.05 just to make sure that the velocity will be above the surface of the fluid. Yani just a very little small, okay, amount of the velocity offset, just to be on the when we render it, the white water, the foam, the bubble, the spray, whatever attribute we will work with, it will be on the surface, distant of the surface on about 0.05 meter. Okay, so it just will be on the top of the surface. Okay, velocity multiplier, if you want to increase the velocity of the multiplier. Velocity multiplier will make the whitewater splash velocity multiply in this number. So if you want to make the splash is faster, we will increase this number. But usually I don't like to use it because I want the velocity of the particle or the splash will be at the same amount of the velocity of the fluid. Okay, of course the splash the white water can be faster or smaller. To be honest, you have to see source as ocean and the wave, how it usually splash. Okay, when it hit a rock or something, the white water will be faster than the fluid or things like this. Okay, but I will leave it as it is for now. Okay, we have a maximum speed, initial lifespan, the age, how long the particle will live. Let's say 4 seconds. This is 4 seconds. Mean 24 by meaning 4 by 24. Okay, yeah, like 69 frame. It will, yeah, let's say 100. Yeah, it will, the particle will live until 100 4 seconds. Okay, let's hit escape. Let's just hit 4 for now. Okay, advanced, we have the advanced here. We have seed. When we increase this number of bubble, it will give us less amount of the bubble. If we don't want to have much amount of bubble is under the surface, foam is on the surface, spray is on the air. Okay, so let's say we want less bubbles. Okay, okay, let's say we have 10 for example. Now we will not going to have more bubbles. Foam will be the same and spray maybe will be the same. Okay, let's go to the limits. Oh, and the velocity noise, if we want to make some noises on the velocity, but I'm not going to use it. And this we have the limit. If we want the splash to collide with something, we can put it here as a collision sub. Then we will import it. And let's say the splash here will collide with the shape we have. So we have to put the sub shape here and the name of the surface here. For example, I will make it, just go back. Let's go here, battle ship. What we have here, I think, yeah, we have the battle ship. So this is the surface of the ship. We can use this. Okay. So we will use the VTB and also it's called collision. The surface will, the attribute called collision, right? So we'll copy it like this, collision. Back again. Let's go to the whitewater simulation. Let's put it here. I think it was in the boat battleship, yes. What was called VDB, yes. And the name is a collision, right? But of course without space. We have a space here. Just let's delete the space. Now it will collide with the ship. Okay, any particle hit the ship, it will collide with. But I don't want to use this because it will not going to collide with the ship. Yani as a yani we don't care about it now, to be honest. Yani, and we don't want to make it slow. So I will just uncheck it. Okay, but it's there if you want. We have the limit size, all this, and we have the forces, the bouncy of the depths, the how much this bouncy by depths, it work on the bubble when it's under the surface. So it push it to the surface, the bouncy depths. Okay, this is the bouncy, like 13. And when it comes to the surface, after yani, up the surface, it will have the gravity. So the gravity will take over and bring it back again to the surface as a gravity. Okay, so the bouncy is for the bubble that is under the surface, and the gravity is everything above the surface, right? This is the gravity. So we don't have to put a force gravity here because white water solver already have its forces here, and it control the bouncy by depth. This is 0, this is minus, and this is 13. It works until 13, as we can see here. If we can see here. Okay. Or value point, yeah, this is in the half, yani. This means this will be in the half. So maybe it will be like something on the surface, of course. This, oh yeah, this is by depth. So this is under the surface, up the surface. This is on the on the surface, and advected by depth as well. Multiplier by depth. All this stuff you can play with it, but usually I leave it as it is. Let's go to the form now. Let's explore the form. Okay, so let's continue. Now, in the form, first we have the clumping. The clumping is the force that make the particle stick together. For not being like a particle flying on the air. No, it will be more like white water that has a bond together, like the fluid. Okay, the force that makes the particle stay together or move together. Okay, so here the constraint stiffness, how strong the particle will clamping or stay together in groups. Not in groups, but yani to have a bond together. Not everyone move in its way like dust. Okay, because white water has physics like a fluid, right? Not just a dust particle, right? Let's say we will make constraint stiffness 5. We will make the particle stay more together, have a stronger constraint stiffness, bound together. Yeah. Then we have the the neighborhood size, the size of the neighborhood with every particle. What the size, like the circle, it's surrounded to have this bond or this constraint, right? So here it's about 20. Maybe we can make it 40, or let's say 30. Of course, it's better to see to make flip book to see the difference between every one. Okay, maybe I can do this, but first I have to cache. The escape back. First I have to cache the white water source to make it faster. Okay, let's cache it. Save to disk. Let's just Control S first to save the file, then save to disk. Close, and I will back to you after it caching. Okay. So the caching is done. Let's load from disk and let's hit reload. So now, as we can see, it's become very fast. Very fast. Okay. As we can see here, it's become like a bullet. Now we can see everything looks very nice. So let's go back. Let's hit escape. Let's go back here. Of course, this particle as well, the particle here need more particle separation. I should add more particle by decreasing the number of the particle separation on the auto dop network here, but as I said earlier, I don't want to make the scene very heavy. So but you can make it like 0.3, it will be better. 0.3, 0.2, something like this. Okay, so we have the particle here. Let's go back. Now the white water, I think it should be faster now. It should be faster now. You should be faster now. Okay. It's not faster as I expected, but maybe we can make some comparison to see how it's going to be. Okay, we have this here. It wouldn't be very obvious, but let's continue. So as I was saying, neighborhood size, the circle around every particle, the size of the circle around every particle, that every particle inside this circle, it will have a constraint with this particle, right? So this is the neighbor size. The maximum neighbor, how many particle should be in this circle. Here is 40, 60, let's say 80, for example. Here we will have more particle, mean we will see more shapes, right? Maybe let's make this 30 and let's make this, yeah, maybe something like this. Of course, you should do some experiment to see the different, right? Okay, so all this you can find it at, I think you can find it at pop fluid. Basically the white water solver is a pop fluid. It works like the pop fluid. Pop fluid work in the particles and give the particles the effect of the fluid, so it will act like a fluid. So I think it will have same Tesla radius tensile, not Tesla, I'm sorry. Tensile radius, tensile strength, viscosity, constraint stiffness, constraint iteration, particle separation, and so on. So you can find it here as well if you use this parameter. If we use this, as we can see, we have constraint iteration, maximum acceleration, tensile radius, we have tensile radius, tensile strength, and so on. Viscosity also. So basically, this is a pop fluid. Of course, pop fluid not added to a new version. I think 17 or 17.5. Okay. So this will be the same. Okay. So erosion work on the shape of the white water, and it kill the depend on the amount we put erosion strength and preservation strength. So guys, I think I just make a mistake. I stopped the video and I didn't click Grecium, so I think you missed some of it. I hope I didn't. You see what I was talking about here. I'm not sure yet which part has been deleted or didn't record, but I was saying that anyway. I was saying that white water solver work as the pop fluid because, and the clamping is the force that make the particle stick together. Okay, the clamping, the strengths that make the particle of the white water stay together or have a constraint between each other. Okay, and if we want, we can it work as the same as pop fluid. If we can see here, pop fluid parameter and pop solver as well, we will see that we will see that I'm not sure what's happening. Anyway, we will see that we have the same as, let's say, clamping parameter here, same as parameter here, constraint iteration, maximum acceleration, tensile radius, tensile strength, viscosity, and so on. So it works same as pop float. Pop float work usually on the particle, and it gives it effect of the fluid. So usually it's just a particle, but if you want to have the effect of the fluid on the particle as the particle act like a fluid, so we added a pop fluid. So same thing for the white solver, it works same as the pop fluid. It has particle, so it make it act like a fluid, so have the same attribute, right? But of course it has more, of course it has max neighbor, yeah, same as here. But of course the white water solver has more and more parameters like forces inside it. We have the forces, we have the limit, we have the emission, and so on. Not sure if this part was recorded or not. I hope it was recorded. So anyway, so now I was saying that we should make a comparison, right? We should make a comparison. So let's first make disable clamping, and we have a camera here. No, we don't have a camera here. Okay, so let's make flipbook setting. Let's start to see the different. So as we can see here, let's play. The particle doesn't have any strength to clamp, just a particle. It acts like bob network, as if we added a bob network particle that emit from the particle that we import, right? As if we added a bob network, right? No constraint, no physics, no fluid physics on the white water, no constraint. Every particle just move by its own. So let's make another sequence list. Let's make another new sequence. Let's enable the density. As I said earlier, the depth is from minus 0.75 to 0.25, and it's a little under the surface to above the surface. 0.25 mean 25 centimeters, because 1 means meter, a unit. Okay, so let's of course when we now we will have a clumpet, we will have repellents, but I don't want to see the repellents, I don't want to see anything. Adhesion, I don't want to see adhesion as well, just to say the difference. Okay, let's make it 20, let's make it 40, and let's make a new one. Let's pause. So the caching is over. Let me just check. Yeah, the caching is over now. So let's start from this point. Okay, we will make the comparing between this point and then the other. Now we have the clumping. Okay, now we will add more constraint to see its effect, but this time I will make only let's say 25, so it doesn't take much time or long time. So make new sequence. Let's make a new flipbook and let's hit start. So let's see the difference now, here with 5 and here with 10. Not much, not big difference as we can see, but maybe it show in another example. Okay, so let's now make this 40 and make this 80, and let's hit a new sequence. New sequence. Let's make the flip book. Let's start. So let's continue. Now after we increase the neighborhood size and the maximum neighbor, this with and this without. So let's check this, and this is the other. So let's check if there is a different. There is no such a big difference, but of course in this example we're not going to see its real impact. Yani its real impact can be more thin on the surface itself, on the surface of the water, when the white water hit the surface and make some white water and foam and these things. Okay, most of it I think is like a spray, so it's not going to be very thin. Okay, we cannot see much in this example. Okay, but anyway, as we can see, the different small max neighbor size, max neighbor size, not a big difference. Okay, so let's make a new sequence. Let's now add the erosion. Okay, let's add the erosion. Let's make it erosion strength something big and preserve strength something strong. Okay, as I said earlier, erosion will kill the particle in a specific way. It's like erosion. It kill the particle that has less density and leave the particle that has more density. Okay, or the white water of the foam that has more density. Okay, so it will leave it like as circles and small amount of particle separation. Okay, so let's make a new flip book to see its impact. Start. Okay, so let's see the impact of the erosion here. This is without erosion and this with the erosion, so we don't see much. But as I said earlier, maybe this sample is not the perfect example for the white water different or compared, because it's just a big amount together. That's why. Okay, so maybe this is not the perfect. So let's continue. There is no different, almost no different here and here, as we can see, just in the small amount. Make some different in just a small amount. Let's make a new sequence. I'll make this 0.5 and maybe 0.9, and this will be 0.9 as well. That means most of the particle will remain, not going to die, at least the density. This is about the preservation strength when it's small like this, it will leave only the density, the particle that has a big density. Okay, and it will kill most of the particles that has less density or small density. It will all will die. Okay, but if we put this, most of the white water density, doesn't matter small density or big density, it will remain. Okay, so let's make another example for the repellents. Let's go for maybe 2 to see the difference. Yeah, so this point it doesn't represent the particle, it represents the repellents. It represents the repellents. If we want to see it, we can see it here. Show repellents. As we can see now, we can see the repellents as a sphere. Also, we can visualize it as a color, alpha red, white, red, and so on. Doesn't matter. Repellent size, if you want to change the repellent size. Now we can so this feature size range, it will be between half a meter to almost 1 meter, the distance. Okay, it has advance, of course, and I will explain this as well. So this is the repellents first. If you want to make the repellents, the function of the repellents, that it gives the white water the shape that we know. It make some noise in it. Some is empty. Some have circle, and so on. Not just a splash of white water. No, it has a hole inside it, right? So it is the thing that gives the white water holes inside it, as we see it in the beach, for example. Okay, so let's make it maybe 0.1 to 0.5. Okay, if we go back, so as we can see now, we have many other repellents particle. It cover a small area, so it will make a small area from 0.1 to 0.5. Okay, and this is a strange range, the strange range of the repellents. On the 1 it will be 10, and on the 0.5 will be 15. Okay, and the noise range between 0.0 to 1. Let's make it 0.5 to 1. Pulse frequency range, it give so pulse frequency range, it will give a movement to the shape of the noise, meaning it's not going to be still, the hole not going to stay still, but its shape will change by time. So if we want to see it, maybe we can put it on 0.2, something like this. Okay, life range, the life range of the, if we want to have a life range for it. And also we can control it from here, radius distribution, meaning the size range 0.1 will have the full impact or full effect of the repellents. Then when we reach the half, meaning 0.25, it will has no strength. Then at 0.5 it will have strength again back. Okay, so we'll have almost the effect will be only on 0.5 and 0.1 and 0.5, no in between. The in between number or sizes will not count because we disabled here, right? And here is also repellence by speed, repellation by acceleration, repellation by depth, and so on. Okay, you can explore every one to see the different, but let me disable this repellence. We don't want to see it, but of course all this particle is a repellence. Okay, maybe we can make it from 1 point. Yeah, okay, that looks good. Small particle. Uh, Noise before. Okay, make it 5. It's okay, make it 5. Okay, so let's make another render new sequence. We already have a new sequence to see its impact. Let's flip book. Let's start. Apologize for the noise on the background. So let's compare. This is without. Okay, this is without the repellents, and this with repellents. We cannot see really big difference. Also, I moved the camera a little. I'm sorry about that, so it will not be very obvious. But anyway, you can do the compare by yourself. You know now how to make it. So let's make a new sequence. Now let's add adhesion. Adhesion is the force that make the white water stick with the surface of the fluid, meaning it's not going to move by itself, it's not going to drift by itself. No, it will stick on the fluid, on the surface of the fluid that it emit from. Okay, so it's like anti-drifting. It's not going to make the foam drift by itself on the surface. No, it will stick on the surface. So when the surface is stretching or move or drift, the white water drift with it, like there is a glow between the surface and the foam. Okay, that stick the foam on the surface of the fluid. Okay, so we have the control range and we have the of velocity angle. We have the enable depth control to make a depth control, and upper surface only. This will work only on the upper surface, not down the surface of the water. Okay, upper surface only. So this force will apply on the top of the surface, not down the surface. Okay, let's make last flipbook to see the difference. Of course, we're not going to see big difference. As I said earlier, the example is not the best example for the comparing, to make a comparing or widget, but maybe inshallah in other example or project we can make another compare to see it more clear. Okay, so as we can see here, if we make a compare and the last without what it was adhesion, yeah, and with adhesion, as we can see there start to appear details, right? Because it make the fluid attach to the surface, right? So now we started to see more detail, and the particle stick to the surface, right? As we can see, there is no really shape, just a circle or a sphere or organic shape, but in this shape it has more detail, right? So this is the function of the adhesion. Okay, so this is the different. I don't need all of this now. Let's so that was the comparison between all this parameter. Okay, let me hit escape and let's go back at the beginning. So that was comparing, as I said, between all this parameter. I hope it's clear now. We will explore it again in other example. That was the end of this lesson. I hope you enjoyed. If you have any comments, please type it in the comment section. And if you want to support us, you will find a link for Patreon and Gumroad below the video, and your support is very appreciated. Thank you and see you in the next lesson. Have a good day.